So remember, what does the agent do? The agent tries to learn a policy, right? So the agent tries to learn a policy. So and as it progresses, right, as it gets more and more experience, the policy changes over time, right? It start off with learning one way of playing tic-tac-toe. Remember the matchbox? As you keep taking, stones out, marbles out, and put no new beads in, right? As you keep taking beads out and put beads in, the policy will change, right? The probability with which you will take various actions changes. That's the whole idea behind menace, right? So that eventually you learn to play a right way. So pi t is a policy at time step t, and it's a mapping from states to action probabilities, as we already looked at. Right? And the thing to remember is that reinforcement learning is not a single algorithm, right? It's a whole paradigm, right? And all reinforcement learning methods specify how the agent changes its policy as a result of interaction with the environment or a result of experience that you are getting from the environment, right? And roughly the agents change their policy in such a way that in the long run they get very good reward or very high reward. Okay, so that's basically the learning problem. I hope all of this setup is clear. Now, so far I have been talking, informally in some sense about maximizing the total reward or looking at some long-term measure of reward and so on and so forth. Let's now become a little bit more formal about that, right? So the goal of an agent is to maximize what we call the return, right? The goal of the agent is to maximize what we call the return. And so what is the return? Suppose there is a sequence of rewards the agent is seeing, right? Let's say the agent started at time step t, right? Remember, we are interacting in discrete time steps. Let's say you start at time t. So what is the first? You start at time t. What is the first reward you are going to see? It's going to be RT plus 1, right? Yes. So you are at ST and then you take AT, and then what you get is ST plus 1 and RT plus 1. So you are going to see RT plus 1, then you are going to see RT plus 2, then RT plus 3, and so on and so forth, right? So what exactly do we want to maximize in this setting, right? So we want to maximize what we call the return GT, which is defined as follows. Suppose you have what are called as episodic tasks. Remember this term. Suppose you have something called episodic tasks. So what is the thing with episodic tasks? Episodic tasks naturally, break into turns, right? So like trials. So for example, tic-tac-toe, right? You play a game and it ends after 9 moves, or sorry, after 5 moves, right? Basically, so 5 moves for you, 4 moves for the opponent. The game will end, right? It can't go on for indefinitely. Or a game of chess, right? After some time number of moves, it's going to end, right? Or you are running a maze, right? Remember the mice and the maze example that we have. You are running a maze. After some time, it ends. You get to the cheese or you get to the water or something, but the maze ends, right? So these are tasks where there is a well-defined notion of an end point, right? And your interaction with the environment is naturally broken up by these end points, and this stretches, right? We call these as episodes. So from the start to the end point, right, that set of interactions is called as an episode, right? So there are tasks that naturally are broken up into episodes. In such a case, right, the return is typically defined as the sum of the rewards you are getting over the rest of the episode. Suppose you start at time t, right? Starting from time t all the way to the terminal time, right? This is capital T is what we call as the terminal time, or the time at which the final state or the terminal state is reached, right? So the sum of the rewards starting from time t, which is RT plus 1, all the way to R capital T, just the sum, that is your return, and your goal is to maximize the return. So we already talked about this when we looked at the grid world, and we said the robot is trying to maximize the total reward and so on and so forth. Now I have made it more formal, right? So when I say return an episodic task, then I mean the sum of the rewards, right? Alternatively, we could have tasks which don't have this natural episodic structure, right? We have an example of something that we have already seen, riding a cycle, right? So I mean, it's not like I want to ride a cycle only for 10 time steps and I'm okay with falling down after that, right? I really like to stay balanced on the cycle for an indefinite amount of time, right? Notice that I don't really mean I want to cycle for an infinite amount of time. I don't really mean I want to cycle for an infinite amount of time. What I'm saying is that I don't have a natural end to this whole cycling business, right? It can actually extend over an indefinite period of time, and therefore I don't want to assume that I can actually write down the sum in a finite manner, right? If I have a finite number of terms, I can write the sum and it will stay finite. Right? Now if I say that my sum can run indefinitely, so there is a chance that the numbers can become very, very large. Right? In such scenarios, right, what I want is to have a mechanism for controlling how large the sum goes. Right? I want to have a mechanism for controlling how large the sum goes. So we use this concept called a discounted return. Right? We use a concept called discounted return. So what does that mean? So I start at time t, right? So I'll take rt plus 1, I'll take it as it is. But then the next return, I'll discount it by a factor gamma. Right? Now gamma is typically chosen to be between 0 and 1. Right? So if gamma is say 0.9, then I get only 90% of the reward at time t plus 2 when I am counting from time t. Notice this is very important. I am counting the reward from t going forward, right? So at that point, at t, I will count the reward at t plus 1 fully, I will count the reward at t plus 2 0.9 times, I will count the reward as t plus 3, right, because I do gamma square, right, 0.81 times and so on and so forth. Right? So what happens is, if the reward comes too much far in the future, if the reward comes too far in the future, then it will get discounted significantly. So even if I sum to infinity, right, this summation will be bounded. This summation will be bounded and it will not run to very large numbers because I am using a gamma less than 1. Right. So what happens if I use a gamma that is 0? Right. So all these terms will go away. I will only have RT plus 1. That becomes like immediate reward problem. Right. If I set the gamma to 0, it will become like an immediate reward problem, but only like an immediate reward problem. It is not yet an immediate reward problem. Right. So why is it not an immediate reward problem? Gamma equal to 0, is it an immediate reward problem? It is not. Why? Because even though I am not looking at the successive rewards, what is the state I am going to see next, right, is still determined by the action I take now. Right. So that is not quite the immediate reward setting. Right. Immediate reward setting, we said, okay, you take an action and then that's it. Right. Then you are presented, if it's a contextual bandit, right, you are presented with a new context that is in no way controlled by what you saw earlier. But in this particular instance, even if gamma is 0, because it is quote unquote a full MDP, so the next problem that you see will depend on the action you took. So there is a slight difference. But gamma equal to 0, you are being very short sighted. I do not care what reward I get in the future, right? I want to make sure I get the highest possible reward at time t. Right? So that is what gamma equal to 0 means. On the other hand, if gamma equal to 1, right, and gamma equal to 1, what do I mean? So basically it is back to the original setting, right? So gamma equal to 1, it is back to this setting, right? Gamma equal to 1 is back to this setting. And that means that I am not going to discount the rewards that come in the future. So however far into the future the rewards come, right? However far into the future the rewards come, I want to count that fully, right? I am not going to keep discounting it. I want to count the reward fully, however far into the future it comes, right? So that is a problem, right? So I do not set gamma equal to 1 unless I am sure that this summation is not running to infinity, right? I am sure that this will stop at some time capital T. In such a case, I can set gamma equal to 1. In all other cases, I set gamma strictly lesser than 1, but it can be 0. Okay. So sometimes people say that as gamma goes to 0, you are short sighted. The smaller the gamma is, you are not looking too far into the future, and as gamma goes to 1, you are far sighted. Typically when gamma is 1, you do not care how far away into the future you get the reward, but you want to account for that also, right? In fact, originally when people introduced the notion of gamma into the return, right, it was more motivated by this trying to look at short-sighted, far-sightedness of human decision making. Remember, we are talking about behavioral psychology, right? So RL was motivated by behavioral psychology. So the gamma was introduced to control for that, how far into the future you look. And then later on, people kind of figured out, oh, okay, adding gamma helps us keep the sum bounded, and therefore there is a proper rigorous mathematical reason for doing gamma, this kind of a discounted return, right? So regardless of what we are defining as, right, whether gamma equal to 0 or 1 or whatever, we want to maximize the expected reward, right, expected value of GT for each step t, right. So GT obviously you can see is going to be a random variable, right, because of the stochasticity, this the sequence of R's I am going to see will vary from time to time. Even if I do not change the policy, if I take the same policy, right, the same state at time t, same policy from t onwards, and I run one trajectory, I will get certain set of rewards. I will run the same trajectory again, I will get a different set of rewards, right. Even if my world is deterministic, if my reward is stochastic, that things might change. Therefore, GT is a random variable. So the value changes from episode to episode. And what I am interested in is taking the maximum of the expected value of GT, because the stochastic nature of the world, right. And I want to do this for each time step t, not just for some t, one t. I want to make sure that I have the maximum reward, maximum return in each time step t. And the goal now becomes to find a policy, right, that gets the maximum expected return at every time step across all policies that you could define on this MDP. Okay, I hope that makes sense.